this demo, we'll use a 2D only version of the water body shapefile and convert that to 3D using conflation to perform hydroflattening. I have the same data loaded as before, except this time a 2D only version of the water body's shapefile. Similar geometry, just no elevations on the break lines. We're going to add a new point cloud task using the task type conflation and the task name water bodies. First, we need to define the input geometry, the source for the break lines. And we can either select, in this case, a shape layer. Since this is already loaded as a shapefile into LP360, it will be recognized as a shape map layer. Or if it hadn't been actually added to the LP360 project and was just in a folder, you could add it as a file, in which case you would get the choice to browse to that folder. So either way is the same result. The conflation input LAS layer is the LAS layer that we have loaded. For output geometry, I'll designate a file. I'll put it in my working folder and we'll call it my 3D break lines. One important thing I'll point out, and this is not only for a conflation task, but any point cloud task that uses the I/O manager, when it writes output, you have the choice to either overwrite or append. So in the case of append, I could, for example, if I was digitizing or somehow creating my output geometry a step at a time, I could continue adding it to an existing output file. Or I can choose to overwrite, in which case each time we'll refresh the contents of that file. Next, I'm going to choose the source points. But before I click on the dialog, I'm going to change my display to display by class and look at all points so I understand what it is that I've got to work with here. So I'm obviously going to use ground points as source for this task. Water's already been classified, so I'm going to go ahead and include the water points as well, because I'm trying to extract elevations around those water bodies, so I want to consider the points that have been classified as water. And I'm also going to choose class 10, which is the buffered ground, and that's not going to be exactly obvious at this time why I'm doing that or what those points are, but later in the lesson you'll understand how those points have been classified in this data set. And notice I just reopened my project, so my labels have not been edited, but the class 10, remember in the previous exercise we changed the label to ignored ground. Next, I need to decide how I want to treat data types. Let's take a look at the attribute table for this water bodies field before we make a decision. So as before, this is the same file without the Z elevation. So we have pond or lake, island, and river. First, under data type, I'm going to select the water type field, and now I get the 3 types listed, and I can specify the conflation algorithm for each independently. The most simple is pond or lake, so let's do that first. Pursuant to the things we've discussed up until this point, we want to put one elevation on the entire lake polygon. So I'm going to choose the conflation method of summarize Z. This gives me some choices as to how I would like to select my Z value. I want to create a flat 3D feature with the same Z on the entire polygon. So I'm going to select that option. And now it gives me some choices as to how I would like to search the surrounding points and consider all of the possible Z values. For pond or lakes, I'm really not interested in capturing the actual water elevation. I'm mostly interested in making sure that it is lower than all of the surrounding ground. So I'm going to say look at all the Z values and choose the minimum. And furthermore, when you're searching, search entirely within the polygon to find the lowest Z. This ensures that our lake will act, hydrologically speaking, as it should within the surrounding DEM. Also, just as a note, if, for example, we were doing a hydrologically enforced DEM and we had some specific constant Z elevation, we had external information about what the water stage might be in a reservoir or a stream, we could actually set that constant Z. For islands and rivers, I'm going to use the conflation method DRAPE to simply extract elevations from the LiDAR surface. I don't have any particular information about the vertices in this shapefile, so I'm going to say use pure drape, in which case it will just intersect the existing geometry with the tin surface, with the triangles. At this point, I'm ready to go. I'm just going to check my output file. Remember, I specified this earlier to create a new shapefile in my working folder. I'm going to put it in overwrite mode, and I'm going to go ahead and select Add to Map when it's complete. And I'm going to copy the attributes from the input shapefile to the output shapefile. All I have left to do now is apply to save, and I'm going to go ahead and apply to the entire project. For some reason, this wants the LAS files to be open to read-write, but frankly, I'm not exactly sure why that is, because we're not planning on editing anything, but we'll go ahead and open the LAS files for read-write. And now we can execute the point cloud task on the project.